Welcome to this chapter of our CUDA Developer Tools video series. My name is Bob Crivella, and I'm on the Solution Architecture team at NVIDIA. In this video, I'll be going over the SOL section in Nsight Compute, our primary profiler for GPU CUDA kernel analysis. The SOL section is the first section of profiler data that will be included in standard or default Nsight Compute output. SOL stands for speed of light, and that refers to one of the key ideas that this section tries to communicate. How is the code performing, or what is the device utilization compared to relevant maximums? The reason this section is presented first by default is that these comparisons to relevant maximums can be a good starting point for selecting directions to investigate when trying to understand or improve the performance of your code. A typical question to ask is, what is the current limiter to code performance? Which is usually one of the cyclical questions asked during an analysis-driven optimization exercise. The SOL section can help begin to answer that question at a high level. The SOL section is also easy to capture or generate because it is part of default Nsight Compute reporting. If you profile your code with the NCU command line or CLI tool and no options, the SOL section will be part of the default output of the CLI tool. Likewise, when processing a profiler report using the GUI tool, the SOL section will be included by default in the output. Like other profiler reports and sections, the SOL section will be created separately for each different kernel invocation that you profile. The SOL report presented by the CLI tool is by default less detailed than the report presented by the GUI tool, but you can get additional information using the -print details all profiler command line switch. During this video, we will be profiling this code. The kernel is very simple, basically computing a norm CDF math function provided by the CUDA math library for an array of vector type. Note there are two variants, one using double type and one using float type. We will compare these. If we profile the double variant code using the Nsight Compute CLI profiler on a GTX 1660 Ti on CUDA 12.0, we get output like this. Similar information is available in the GUI version of the profiler. One method to use the GUI version is to generate a profiler report using the -O switch for the NCU CLI tool, and then copy the report file to a machine that has the profiler installed in a graphical desktop environment and import the file there. If we use the GUI, we see the following for the speed of light report section. Note that these listed metrics and measurements correspond to the CLI output. In the GUI version, there is more information available for this report section. We can expand the section by clicking on the triangle button to the left of the section title to reveal additional information available for this report section. In addition, we can get additional information about a measurement or metric by hovering the mouse over the metric as we see here. In this case, we can see that the DRAM throughput metric refers to measuring traffic between the GPU itself and the DRAM attached to the GPU, and the measurement is expressed as a percentage of peak achievable. Now let's revisit the previous report section view and talk about the various components. The measurements and metrics at the top are the same as those reported in the CLI report section. The compute SM throughput measurement gives an indication of SM activity level as a percentage of peak achievable. A high number here is both a good thing to attain as well as a general indicator of where to focus to make improvement. We'll see an example shortly. The memory throughput measurement indicates the level of activity in the GPU memory pipeline as a percentage of peak achievable. The L1 text cache throughput presents a similar measurement for traffic to the L1 text unit, and the L2 cache throughput measurement indicates the level of traffic flowing to the L2 cache as a percentage of peak, and the DRAM throughput indicates the level of traffic to the GPU off-chip DRAM array, as already mentioned. Moving to the column of measurements on the right in the top area of this report section, the duration is the measurement of time elapsed that the kernel consumed, measured in milliseconds. The elapsed cycles line is a similar measurement expressing the kernel duration in terms of elapsed GPU core clock cycles rather than milliseconds. These two numbers are related to each other by the SM frequency indication, such that the elapsed time in nanoseconds multiplied by the SM frequency in cycles per nanosecond should be approximately equal to the elapsed cycles. The DRAM frequency indicates the DRAM clock speed expressed as clock cycles per nanosecond. This is an indication of transfers per second frequency, not the base clock frequency of the DRAM. So the pumped characteristic, in other words, transfers per clock characteristic, of modern DRAM increases this number. Finally, the SM active cycles indication represents the number of elapsed cycles during which at least one warp was active. This is upper bounded by the elapsed cycles indication. If we study the measurements discussed so far, we can see that for this particular kernel, the SMs are quite busy, but the memory traffic is relatively low, expressed as a percentage of peak achievable. The memory subsystems are not very busy over the kernel duration. Therefore, the kernel duration is primarily driven by compute traffic, not memory activity. If we want to improve the performance of such a kernel, in other words, shorten its duration, we will need to seek ways to reduce the compute load. Reducing memory traffic or improving memory utilization efficiency is not likely to yield much benefit in this case. Let's cover the remaining information presented. The next item in this report section is an indication of high throughput. This particular part of the report section is an output of a rule in Nsight Compute. Rules in Nsight Compute can be used to process metric data and measurements and give text that includes analysis or assessment. Nsight Compute has a number of available rules, and this particular one is telling us that we have one subsystem, in our case SM Compute, that is above 80%, indicating it is highly utilized. If we are going to improve our kernel performance, we will probably have to address this by shifting some of that load. So this rule output has confirmed what we had already conjectured, based on study of the individual metrics and measurements. Furthermore, the rule text is pointing us to a different report section that may have information useful for next steps. The rules output is extremely valuable, especially for beginners, because it analyzes data based on expertise provided by the Nsight Compute development team, effectively a kind of expert system. Pay attention to rules outputs, which can range from information such as this one to warnings, which indicate more important performance issues. Moving on, the next part of this report section depicts bar charts showing the relative utilization of compute throughput and memory throughput for this kernel. These are basically the same numbers as the compute SM throughput or memory throughput numbers already covered, expressed graphically. Moving on, the remaining section area has detailed metrics organized into two columns or categories. Up to this point, the characterization provided in this section has largely been to indicate a comparison between compute throughput or utilization and memory throughput or utilization. The remaining columns of metrics further subdivide and characterize each of these two categories. Taking a look at the column on the left called Compute Throughput Breakdown, we see that the word pipe appears frequently. The characterization of the compute throughput is now broken out by individual pipes. You can think of a pipe as a functional unit inside a GPU or GPU SM that processes certain types of instructions or operations. For arithmetic work, for example, we might have different pipes or functional units that process integer operations versus floating point operations. In fact, the individual pipes reported include 64-bit floating point, 32-bit floating point, integer operations, and tensor core operations, as well as other types. Again, you can get individual descriptions by hovering the mouse over the measurement title of interest. For this code, we see that FP64, i.e. 64-bit floating point operations, are the most significant consumer of compute throughput. So the takeaway previously was that we wanted to consider whether we could shift the compute load elsewhere. And in this area, we now know that the compute load that we want to shift is 64-bit floating point compute. Our code makes substantial use of 64-bit floating point operations in calculating the norm CDF function. And furthermore, the GTX 1660 Ti device has only a relatively small number of 64-bit floating point compute units to handle this type of work. The combination of these factors results in this characteristic of our code being the long pole, the thing that we might focus on to improve performance. Taking a look at the column on the right, called Memory Throughput Breakdown, we see that similarly, memory subsystem utilization is now further characterized into specific types of activity, spanning various aspects of the memory subsystem, including DRAM, L2 cache, L1 text unit, the load store unit, and other mechanisms. Our previous high-level characterization from this report section indicated that overall, memory subsystem utilization was low for this code, and we see this reflected again in these detailed metrics. So is there anything that we can do with this code to change its behavior? We've already discussed some possible clues. The profiler has indicated that compute utilization is the long pole, or the bottleneck. Furthermore, the profiler has indicated the specific compute pipe of interest, that is, the bottleneck, is the 64-bit floating point pipe. We also know that the GeForce GTX 1660 Ti has relatively limited 64-bit floating point throughput or capability. A simple change we could make to this code to see how behavior and performance would be affected would be to switch from using 64-bit floating point to 32-bit floating point. This means we will be using float quantities instead of double quantities, and that we will use the 32-bit floating point version of our norm CDF function, called norm CDFF. The code is already set up to make that switch by compiling without the use double define. When we do that and reprofile the code, we see a report that looks like this. We can make a number of observations about this. Before we do that, let's use one of the basic features of the UI reporting called baselines. Setting a baseline in a report tab causes that report tab data to be used as a reference point when we are looking at other report tabs. Here we see that I have a report tab for the previous report we were looking at and a report tab for the new version of the code that uses float instead of double. If we go to the previous report tab, click the Add Baseline button at the top, and then switch back to this report tab, we see output that looks like this. Now we effectively have our old and new data presented in comparative fashion in a single report view. This makes it easy to see where the biggest changes were from the profiler's perspective. So what has changed? First of all, we see that the kernel duration has gotten dramatically shorter, going from about 2.71 milliseconds in the double case to about 63 microseconds in the float case, a reduction of over 97%. The profiler is also telling us that our code is balanced, meaning that both compute and memory utilization are taking place in roughly equal relative amounts when compared to the peak theoretical offering on this device. Previously, we had an unbalanced code where the 64-bit floating point was the limiter to performance and the memory utilization was relatively low. We see this in the bar chart summarizing this, where the green bars correspond to the previous report, now used as a baseline, and the blue bars represent the current report. Our rule output is telling us the same thing, that we have balanced throughput. Looking at the detailed metrics, we again see confirmation of this. Switching from double to float has changed the computation and therefore the pipe used from 64-bit to 32-bit floating point. We see now in the compute throughput breakdown that the FP64 pipe is no longer utilized, but the pipe referred to as FMA is now the most active. The FMA pipe is the one that handles 32-bit floating point calculations. We can make the observation at this point that the ordering of pipe activity in this report section is not fixed, but is arranged in Pareto order. Therefore, the ordering in the report changes depending on which pipes are most heavily utilized. This change in the kernel has had several impacts. First of all, we know that 32-bit floating point quantities take up half the space of 64-bit floating point quantities. So this variant of the kernel is loading and storing half as much data. However, the kernel is also dramatically shorter in duration, due primarily to the change in compute pipe utilization. Comparatively speaking, our GTX 1660 Ti device has much more capability when processing 32-bit floating point quantities compared to 64-bit floating point quantities. So the huge reduction in duration of the kernel means that even though we are loading and storing only half as much data, the overall time period during which that load and store activity is taking place is much shorter. The result is that our memory utilization, actual traffic versus peak theoretical, has increased substantially from a number in the 3 to 4% range to a number that is over 70%. Since both compute utilization and memory utilization are relatively high, this kernel is balanced. This is just one report section that is available in Nsight Compute. It is considered the starting point, the report section that merits your attention first. So it is presented first in Nsight Compute reporting, but there are other report sections. The rules output in this section, combined with what you have learned about using this section, can help direct you to other report sections to investigate next as you continue your code profiling and optimization journey. Check out our other videos that detail these other report sections in Nsight Compute, as well as all of our developer tools from the link in the video description.